All right, Tara, so I'm looking at your email, and I sent you an email saying that it's kind of complicated to try to figure out a way to actually address everything in it, so I'm going to try to do so via this movie. So in your first paragraph, as I'm looking at your first paragraph here, I'm noticing that you mentioned something about the charge of HCl. This is actually irrelevant and does not at all play any role whatsoever in this question. And so I think that by you're overthinking this. Well, no, maybe you're not overthinking it. Maybe I'm kind of catching on to what you're saying. So if you have the totally deprotonated base, I'm going to draw down here a titration curve, right? Where over here it's a pH. Let's try that again. And this would be the HCl that you add. And as you're doing this, you're starting with the totally deprotonated tyrosine. So think about what that means. It means that your amino group is NH2, the side chain is O minus, and the alpha carboxyl group is deprotonated as well, so it's COO minus. So you have those three groups. The side chain has the highest pKa, then the alpha amino group, then your carboxyl group. So if you were to draw this titration curve, you hopefully would know that since everything's deprotonated, in order for it to be deprotonated, you would have to have the pH far above the highest pKa in order for that to happen. So you should have a really high pH. So you're going to start with a high pH. And as you move down the curve, you come into your first pKa zone, where it's kind of flatter and you get the midpoint. Then you have an equivalence point. Then it comes again. You get my drawing's not so good. And then you get another flat area again where you have another midpoint pKa. Then you get another equivalence point. And then another pKa, and then another. So you have one equivalence point, two equivalence points, three equivalence points. And this question is asking you about a pH that's about pH 3, and if you look, I think you're the only pKa that can be within one pH unit is the pKa for the alpha carboxyl group. So as we go through this, and here's what I think you were referring to, the HCl. So let me just draw this real quick. Remember what an equivalence point is. An equivalence point is a point on the titration where all of your starting titrant, all the moles of the titrant have been used up. And because you have three titratable groups, you're going to have three equivalence points. Each one takes the same exact amount of HCl in order to react with all the base and fully protonate it. So at this first equivalence point, you've added enough HCl to protonate the side chain. Then here you've added enough to protonate the alpha amino. Sorry, I'm doing this on my phone and I'm having trouble here. And then the last one would be the carboxyl group. But however, you do not get this far in the titration. And that's because you're not going that low in pH. You're going to, I think it said pH 3 or something like that. I don't have it right in front of me. So in order to get to pH 3, you have to have enough HCl added to fully titrate the side chain, to fully titrate the alpha amino group, and then just enough to take the carboxyl group and make it so that part of it's protonated and part of it's not. So you have to review your titration curves. And what does an equivalence point mean in terms of the amount of HCl you add? You're going to find out that the same number of moles of HCl added equal the same number of moles of starting tyrosine. So in principle, this amount should equal that amount. So you should have essentially what we'd say 2 equivalents of HCl added before you can even begin this part, which is then a buffer part. So that's where I'm going to go. This stuff you have here, I'm not so sure I can even make sense of it right now, but I'm hoping that if I help maybe set the framework for the problem, you might be able to do this. So this would be what you would get for titrating fully titrating all of the available amino group. Side chain. This would be all the available amino group. This would be the amount of, right up to here is just enough, just the right amount of HCl to create enough COOH so that you have COOH and COO minus to make your buffer. See if this helps you. Although as I look at the mess I just created, I'm not so sure. But the idea is it's a little more complicated than simply using that. So once you figure out how many, essentially, this tells you how many moles of HCl you need to titrate the first one. This tells you how many moles to titrate the second one. And then the amount of moles of HCl that you need to create the buffer itself, to create the COOH. You add all of those together and you get moles of HCl. And once you know the moles of HCl added, because all the protons that are being added to this titration are coming from the HCl. That's why you can do that. Then once you know all the moles of HCl that you need, then you can use this formula, which is concentration of HCl times the volume of HCl is equal to the number of moles. Now this has to be in molar, this has to be in liters. And this will, of course, will be in moles. Well, think about it. You'll calculate that from the analysis I just talked about. That's 8 molar because I gave that to you. And then this represents the volume you'll add. So that's how it works. See how you can do. Maybe the other thing you might want to think about is how do you calculate the starting number of moles of tyrosine? In fact, why don't you send me an email that shows me how you calculate the starting number of moles of tyrosine? In fact, you may have that right there. 0.25 liters times. Yep, that'll tell you how many moles of. So you're doing this part wrong here. You multiply because you don't have. Okay, I'm going to switch to one more slide to give you another look here. No, I'm just going to stretch it out. Here. So you were given, I think, 15 millimolar, which is 0.015 moles per liter. And you know that you have you know what your volume is in liters. So see if, and you know you have what? Your volume I think you have is 0.250 liters. So you need to figure out how many starting moles of tyrosine you have. Then that equals the amount of moles you need for each equivalence point. So see if this information at all is useful to you. Hopefully, if it's hopefully I didn't confuse you more than I helped you. But given the nature of what I saw in your email, I could tell you were so confused, and so many of the things you had suggested were betraying that fact, and I want to make sure if I can help you rethink your starting point. You may just want to start from the beginning using the information that I provided. Strategy would be calculate how many moles of H need to be added to create the buffer. And in order to get that, you have to go through 2 equivalence points and then part way into the third. See if that helps.